Of NMF and topic modeling, so we're going to finish up with the last little bit of that. Actually, we'll probably only need the first half of the lecture to finish up for that. And I'm going to try something a bit experimental this time with the class. So for the second half, we're actually going to talk about clustering and approximation stability. So it'll be a way for me to draw out one of the important themes in the class, especially in this unit, which is to what extent does well-posedness of the problem, can you exploit that to get better algorithms? So it'll be one other example. Separability is something we've been discussing so far, and approximation stability will be another example. But if you remember last time, where we finished up was this probabilistic approach via Bayes' rule to doing anchor word-based recovery. So, just to do that, just to remind you where we are, so the crucial definitions that we introduced last time was that G is this gram matrix. It's this word-by-word matrix, which is a probabilistic version of the usual gram matrix, in which the entry in row J, column J prime, can anyone remind me what that was? What do we define it to be? Yep.
First word is J, probability first word is J, and second word is J.
Exactly. So it was the probability under a randomly, in a random document, which was generated by our abstract topic model, where you generate the columns of W stochastically, what each document is a mixture of topics, and then you multiply that column by A to get a mixture over words for each document, and you do independent draws from that distribution. So it was the probability that in a random document, the first word is J, and the second word is J prime. And we also had this other crucial definition. So this is a matrix which, when we take a large number of documents, we can estimate empirically what these probabilities are, because we can just look and see what fraction of documents this holds. But there was another useful variable, which in our case was Ri I prime, which is this topic by topic co-occurrence matrix, in which the entry in row I, column I prime was just the probability that in a random document, the first word is generated from the ith topic, and the second word is generated from the I primeth topic. So this was our way of thinking about each word generated from a document. We first choose which topic it comes from, and then we choose which word. So it's as if we annotated each of the words in our document with what topic actually generated them. So we can't see these random variables, but this is still a useful thing to define, because we had this sort of powerful relation that this gram matrix is just A times R times A transpose in our abstract topic model. So do you guys all remember this? Yep. All right, so where we were last time was, what we did was I did a sequence of derivations which allowed us to set up a system of linear equations to solve for probability of topic given word. That was the basic idea. So, I just want to put up those equations again and give you an opportunity to, ask further questions about that before I piece it together to give you the overall algorithm. But if you remember, it was just a pretty simple derivation. So using Bayes' rule in a few clever ways. So we started off with this quantity, which we can compute from our samples or approximate from our samples. And expanding it by the law of total probability, we had this version where we're just marginalizing over what that hidden topic is, topic 2 that actually generated word 2. But the first step, which you need to sort of rationalize, is that this term right here is actually simpler because it doesn't depend on what the second word actually is. So does going from here to here actually make sense to everyone? So this will be your opportunity to ask me to clarify this step. Make sense, or anyone want me to prove it?
Isn't it just conditional independence, or what
Yeah.
is there to prove?
All you have to do is, it depends on whether this, all you can do is just compute what this is until you end up with an expression which explicitly is sampling word 2, given that topic 2 is already fixed. And then it is independent, literally, from the model. So this is something that, hopefully you can just prove by thinking about what the model specifies. But there's also this remaining step, which, the other piece that we relied on was actually this statement, that probability that W1 equals J given topic 2 equals I prime is the same thing as the probability that W1 equals J given that W2 is the anchor word for the I prime of topic. So this was the other sort of crucial step in this derivation. So does anyone want me to prove this statement, or does it look intuitive?
Can you prove that?
Can I prove it? All right. Let's do that. So let's prove that. So the way to actually prove this we can expand it in the same way via the law of total probability. Based on what this hidden topic is. But this term right here is easy, right? So if we observe that the second word is the anchor word for the I prime of topic, then this conditional probability is just 1 on whichever topic it is an anchor word for, and is 0 everywhere else. So this quantity right here is just equal to 1 if I double prime equals I prime, and 0 otherwise. So the entire thing we get out is just that this quantity is equal to just a contribution from a single term in this, corresponding to whatever topic it is an anchor word for. And now we can just apply Bayes' rule and expand it. Using exactly the same rule we did before, that once we've conditioned on what the second topic is, that word 2 is actually conditionally dependent. So we can just pull this out, cancel these terms, and we get exactly the relation that we need. So this is sort of the proof of that key claim right there. It's just exploiting the fact that anchor words are extreme in the sense that their conditional probability is just 1 on whatever topic they're an anchor word for, and is 0 everywhere else. So we only get 1 term of contribution. So that's sort of the main cleverness in this, is just this key step right here, because now we actually get the expression we were interested in the first place. So this is where I finished up last time. So we can apply this, which we just proved. And what we can end up getting is that the remaining sum now gives us a set of linear equations in these unknowns. So, the thing to convince yourself of is the left-hand side we have access to. We can estimate it to arbitrary accuracy just by taking more and more short documents. And once we know the anchor words, we can also plug in what those constraints are, what those values are, and we get a linear system in these unknowns. And sort of key property that I'm just going to assert but not prove is that it turns out that if R has full rank, there's a unique solution to the linear system. So this allows us to get almost all the way done, is we can compute the probability for each, of probability of topic given the word. And what we really want is we want probability of word given the topic, but now we can finish up the entire thing with Bayes' rule. So does this make sense? Or are there any questions about this? This is also in the notes online, so you can find it there. But now let me state how we're going to use Bayes' rule, and then we can actually state the full algorithm. So let me call this expression 1, because we're going to solve it for probability of topic given word. And finally, by Bayes' rule, we get probability of word 2 given topic 2. With this expression. So this bottom part is just the probability that topic 2 is I prime. So I'm just expanding whatever that is via the law of total probability again. And the important thing is that now we can compute this top part based on expression 1, because we can compute each term. This is something that we have access to just from the statistics about documents we're given. And this we can also compute. So the reason for sort of plugging in this expression is that otherwise I don't know how to compute the probability of, say, topic 2 equals I prime. But this gives me a way to compute it based on the things I know already. So now all we can do is we can use this equation to actually compute the entries in A that we're interested in. So now the full algorithm, simple to state. So we'll call this the anchored Bayes algorithm. So we compute the grand matrix from our data. going to crucially rely on the algorithm we developed for separable NMF, because what we do is we compute the anchor words by solving separable NMF. This is exactly what we did in the last lecture, was we gave geometric interpretations of the anchor words being extreme points, and we gave a simple algorithm based on linear programming to find them. Actually, I posted the homework today, so it'll be due March 5th. And the last question of the homework asks you to analyze a simple greedy algorithm for finding the anchor words instead. So its proof of correctness is roughly the same as for the linear programming approach, but it's a much better algorithm to use in terms of its running time. And ultimately, what we do is we just use the anchor words. We solve one for these unknowns. And then we use 2 to find the entries of A. So this is our full algorithm. And so the important point about this algorithm is that, so the way I've analyzed it is in the exact case. You know, when you're actually given access to all of these entries perfectly. Now in reality though, all you're going to do is you're going to get additive approximations to these things. You know, you can estimate each of these quantities within an additive epsilon just by naive Chernoff bounds by taking enough documents. So the way to think about it is that, you know, you should convince yourself that actually this analysis would go through with more work in the case where we were given noisy access to these quantities, and that you could bound how well this algorithm actually finds the entries of A. That is, that these estimates it comes up with converge to the true answers at an inverse polynomial rate as you take more and more documents. Because as I take more and more documents, I get a finer approximation of this. One of the things you have to prove is that when you only have noisy approximation to these quantities, instead of finding the true anchor words via separable NMF, what you can do is you can find things that are close to the anchor words, and they converge to what the true anchor words are. And then you solve this linear system with noisy entries instead of the true ones. But what you need is that this linear system is well conditioned and that the errors don't magnify too much. And the same thing goes for plugging into the Bayes rule. So I'm only going to do the analysis in the case where you have exact entries. But something you should be aware of is that the types of bounds you really want are that if you want some target accuracy epsilon to all of the entries in A, you want to bound on the number of documents you need, and you want to bound on the running time of the algorithm. And I'm just asserting that these things can be done. But the main theorem for this is that there is a polytime algorithm to learn the topic matrix for any separable topic model. If R is full rank. And this full theorem in terms of what the dependencies are would be kind of a pain to state. But you know, I just want to tell you what this polynomial depends on. So the running time and sample complexity they depend polynomially on parameters like m, n, and r. So we have, you know, an m by n word by, well, actually, I guess it only depends on n here. So it depends on n and r, which is the dimensions of A itself. And it also depends on things like the smallest singular value of r, because you need to assume not just that it's full rank, but that its rank is bound, that its smallest singular value is bounded away from 0. That governs how many samples you need to take in order for your estimates in this equation to still give you good solutions, estimates for the true answers. And it also depends on things like P, the probability, the minimum probability of any anchor word, because I need to take enough documents that I'm likely to see many anchor words in the first place. And it also depends on, 1 over P, and 1 over epsilon, where epsilon is the target accuracy that I want to learn for A. And it'll also depend on things like log of 1 over delta, where delta is my failure probability. So this would be sort of the full statement, is these are all of the things on which it depends. But the important point is that, with all these parameters as fixed, there's a polynomial number of documents and running time that you need in order to actually provably get epsilon accurate estimates for any separable topic model. So that's sort of the main result we've been working towards. So are there any questions about this before I tell you about some of the experiments? Yep.
What if we use the fact that G equals AR A transpose, that thing you said right at the beginning? Is that part of this analysis?
Yeah, so essentially to get the statement that if R has full rank,
okay.
then there actually is a valid solution, you use that. Because A, by definition, will have full rank because it's separable. But that's where it comes in. But good question. Any other questions about this? All right. So, we've done a lot of work now to show that separable topic models are easy. What I want to ask now, I think now is a good time to ask, are natural topic models actually separable? So, the difficulty in answering some of those questions is really who's to say what a natural topic model is in the first place. But let me tell you 2 experiments, which are ways of circumventing that question beginning. So there's a very popular data set called the UCI data set. Probably a bit dated by now, but it's a collection of 300,000 New York Times articles, probably from about 15 years ago. Sorry, is there a question?
Yeah. So what is that 1 over P?
Yep. So P here is a lower bound on the probability of every anchor word. So you need not just that they're anchor words, but if they never happen, then you can't really use them. So what's going to happen is that the smaller P is, the more documents you need to take in order to be able to learn what the anchor words are, or near anchor words. So that'll end up influencing the sample complexity, which in turn influences your running time of the overall algorithm. All right, so the UCI database is a collection of 300,000 New York Times articles. And the other thing I want to tell you is that they're very popular topic modeling toolkits. One of my favorites is Mallet, which came out of UMass Amherst, and is one of the maintainers is David Mimno, who was a co-author of mine on a lot of these things. But one of the things you can do is you can train Mallet on the UCI collection. And you can just ask, what does it find in terms of what does it think the topic matrix is? Now, the truth is something like separability is a very rigid constraint, right? Because the way to think about it is that the probability of a topic given that particular word should be entirely concentrated on just one topic. Now, that's a very strong assumption about what a word is, but if you define something like near anchor words, where the probability, the conditional probability of topics given the word is highly concentrated on one word. Let's say there's an entry of at least 0.9, then it turns out that a large fraction of the topics really do have near anchor words. So it turns out when you train it with, R is about 200 topics, that about 0.9 fraction of topics have a near anchor word. And by this I mean that the probability of topic given the word is at least 0.9 for some topic. So even though you don't have words which are perfect indicators of topics, you still have a lot of words, or at least a large fraction of the topics, which have some word that's a very strong indicator for some topic. How strong? When it occurs, at least 90% chance which topic generated. So now, so this somewhat answers the question about, are topic models natural ones, actually separable or nearly separable? But maybe there's a different question that comes to mind, which is, nothing in the world can be perfectly separable, but is this separable enough that these algorithms can still work? So, in fact, there's a second experiment, which is perhaps my favorite in this. So let me tell you about a way to turn this question on its head. So let me create a very biased experiment, which is going to slant the table really against us. See, the trouble with working with real data is that one of the issues is that there isn't necessarily a ground truth. After all, our assumptions about these abstract topic models, they don't perfectly fit the data for sure. But one of the things you can do is you can try and learn a topic model on real data, take that for granted as being a natural topic model, and then you can use it to generate synthetic data, actually from a topic model. So the important thing is that in this experiment, there really is a ground truth, which is whatever Mallet thought was a natural topic model. So now you can generate new documents, and you can ask a very biased question. And you're already taking for granted that the A you're using is something that Mallet already learned. So you can ask the question, can Mallet find its own output again, compared to how well this algorithm we just developed finds A from scratch? And the important thing is that A here is not separable, right? It's just whatever Mallet learned and thought was a natural topic model. And the sort of funny thing here is that actually if you take enough documents, the algorithm I presented is a couple hundred times faster, and yet actually produces more accurate results. So it's sort of a way to flip the it's a way to flip the question on its head, because you're taking for granted what natural topic models are, and you're taking for granted that topic modeling toolkits that people already use do something interesting. But the issue is that why they work could actually be a reason like separability. So the idea is that formalizing when and why things work can actually lead you to faster algorithms that more directly exploit what it is as a structural property that's making the instance easy and not computationally hard. So let me, actually, does anyone have a Mac connector? I'm going to show you the data, and then I seem to have forgotten mine, but do we have any? If not, I'll have you guys come up and we can take a look at it, and then we'll start with clustering after that. All right, let's do that. Everyone come up. We'll get the blood flowing and stretch out. All right, so what I want to show you about this, and I want to emphasize one of the themes here, is that, okay, so what I'm going to be comparing to is that there are very powerful heuristics like Gibbs sampling. So these are Markov chain-based approaches for trying to learn, what are the map estimates for the parameters that could have generated the data. These are heuristics that we're going to get into a little bit later in the class because I think analyzing them in interesting settings is a really nice open question. But it's something which, the runtime really is bad because, as you take, it's not doing something as simple as just basic linear algebraic steps. So, of course, it needs a decent runtime. So I think sort of the surprising thing is not that the algorithms we're comparing to have much smaller running time, but the fact that they actually do produce better data even when the, true topic matrix is not exactly separable. So the algorithm I described is actually recover L2. And what this experiment is because we generated some ground truth, there really was a true topic matrix that generated the data, you can take your estimate and you can ask for the min-cost matching between its columns and the truth according to things like the statistical distance. So all this does, it measures the statistical distance and the min-cost matching between the columns in our estimate and the truth. And what we proved was that if the topic matrix really were separable, that cost is going to converge to 0. So the issue is that because it's not actually separable, it's not really going to converge to 0, but the question is how accurately do you get it? So the interesting thing I find is that approaches like Gibbs sampling, what they're trying to do is they're trying to compute the maximum likelihood estimate. So they're very difficult to compete with in small numbers of documents because maximum likelihood really is the answer to the question, what should you do with your sample limit? And computational intractability is not such a big deal when you have small problem sizes because you can't really get caught in local minima. But one of the things that I find really interesting is that, as you take the number of documents larger and larger, eventually this accuracy is actually better for the algorithm we showed, this recover L2 approach based on Bayes' rule. So I think one of the things that it teaches us is, these days you hear big data, in every talk. Every job talk has big data in it, otherwise you for sure wouldn't get an interview here. But the funny thing is that most of the approaches there are more of a systems and machine learning approach, where we take for granted what are the algorithms that we care about and want to scale up. And the question is, how do you actually scale up those algorithms to work with huge data sets? But as a theorist, I think we haven't even decided what are the right types of algorithms to scale up in the first place. The approaches like Gibbs sampling, which do well on small instances, those are instances in which you don't have to worry about computational tractability, local optima as much. But eventually, for larger and larger problem sizes, the fact that I've changed the problem but made it in a way that I can exactly solve it ends up being more useful than actually a heuristic for solving the exactly right problem to begin with. So the question is also the nature of how bad are local optimum, and are provably good algorithms better? And one of the things which really hasn't been explored is what the right trade-offs between those are as you take larger and larger problem sizes. So this is sort of one of the themes that I want to get out of this first unit. We're going to see a few different themes about the interaction of theory and machine learning problems. So let's take a 5-minute breather, and then I'm going to tell you a little bit about other instances in theory where people have explored this question of does well-posedness of the problem lead you to assumptions that get better algorithms. So that'll be the end of the first unit, and then we're going to talk about tensor decompositions in the second unit. All right, so let's take a 5-minute breather.
So in the second step,
Which second step? Yep. No. Very good question. So the issue is that, so think about separable NMF. So when you find the anchor words, that will find you the unique decomposition A and W only if you're assuming the normalization where the columns sum to 1 for both of those matrices. The issue is that the way that we're actually using the separable NMF is that we're running it on G, which is A times R times A transpose. So if you're grouping together the R and A transpose, that's your W matrix, and it doesn't actually have the same normalization that the columns sum to. So part of the issue is that what you still have is that from this RAM matrix, every non-anchor word can be expressed as a non-negative, actually convex combination of the anchor words. But what that convex combination is giving you with this normalization is not actually the rest of factorization. What it's giving you is explicitly the probability of a given words. So all this step is geometric is it's expressing every word inside the convex hull and the convex combination of the anchor words. And the way to figure out what these probabilities are. So your intuition is good, but that's a subtle point. It's because what you get out of the geometric picture here is not the same as what happened for separable NMF. Because what you really get out of the geometric picture is this, and what you want is the flip. So it's not that far off, but that's why you need a 2-second
What is the corresponding variable to your answer?
What do you mean by that? What do you mean? So you are explicitly taking G and looking at the rows of G.
You're trying to solve in our NMF.
Exactly. Because G is A times R times A transpose. And when you group together R and A transpose, that's not negative. And the first part is definitely separable. But what you're explicitly doing is you're taking the rows of G and you're finding a simplex that contains all of their convex hull. And the vertices of that simplex will be there. But the interpretation of what it means to express a non-anchor word as a convex combination of anchor words is now this interpretation, not the old NMF. So that's a very subtle point, but that's exactly the right way of thinking about it. Yep. All right, so let's do, now that I think the 5-minute break is up, let's do a vignette from clustering. So, the way I want you to think about this is really, theory in a sense is at a bit of a crossroads, because most of the time in theoretical computer science, we study worst case approximation algorithms. We look for what's the best constant, what's the best power of log that we can get some approximation algorithm for some hard problem. And one of the sort of unnerving things to notice is if you look, what problems in the last 15 years are actually in polytime that are surprising that they're in polytime. So I'm deliberately taking out of this question all of the instances of faster algorithms for problems that are already NP, or better approximation algorithms for things that we know are NP harmed. And so it, to a certain extent, the sort of elephant in the room is that so many of the problems that practitioners care about solving, we take a very pessimistic approach guided by computational intractability, that you can't really solve those problems, so why, the only thing you can do is try and approximate them. But this was designed as a way to think about paths around computational intractability. Let me give you another classic example from clustering. So clustering, there was this really influential work of Balkan, Blum, and Gupta. But just to sort of set the backdrop for this, in a lot of applications in clustering, what we're really interested in doing is we're given some collection of objects, and we want to partition them into groups which are like objects. Now, we've already seen some cases where we might want to do that. You could think about, given some collection of documents, how can you partition them into what topics they're about? But there are much more complex ways that you could think about applying clustering. So, for example, you could, in biology, have descriptions of different proteins, maybe based on the pattern of atoms and how they're connected. Or you could even have a description of the shape that they fold to. And you very well might want to partition those collections of proteins based on what their function is on the cell. So the point is that the natural description of the object can be very different can have a complicated mapping to what its actual function is. So it could be hard and take a lot of art to figure out what are the right ways to measure distances between objects, when are they near or when are they far. But in any case, what I want to introduce is one of the most popular problems in clustering is the k-median problem. So in the k-median problem, what we're given is a metric space. So for those of you who haven't seen that before, you've probably, let me just define what it is. So a metric space is just a function from pairs of points in some set to R plus actually R negative is a metric space if for all x, y, and z in this set, we have the following conditions. The distance between any pair of points is non-negative. You can think about Euclidean distance as just the most natural special case of what a metric space is. The distance is 0 between 2 points if and only if they are the same point. And we have reflexivity. And finally, and most importantly, we have triangle inequality that that the distance between x and z is bounded by the distance from getting from x to y and y to z. So, of course, the Euclidean distance gives you a metric space, for example, on the plane. But there can be much more complicated metric spaces you can define. Think about, what's the right metric structure for quantifying how far or how close pairs of proteins are when you want to figure out whether they have similar functions. That can itself be a very complicated distance function that takes a lot of science and physics and chemistry and biology to actually define properly. So you should think of this as a very complicated object you could be given. But in general, for k-median, you're given some set of points, which you want to cluster now. So you're given some subset, S is a subset of X, and D, this metric space. And the goal now is to find a set of centers, C1, C2, up to CK, K of them, because hence the k-median problem, which are in this larger ambient space on which your metric space is defined. But you want to do so so that you minimize some measure of the intra-cluster distances. So there are a lot of variants of clustering problems that are just different ways to measure intra-cluster distances. K-median is one of the most natural ones, which all you do is you map each point in your set to whichever cluster it's closest to in the K things you've chosen, and then you add up the distances. So all you're implicitly doing is you're taking your set of centers, you're looking at the partitioning you get when you map each of the points in S to the center that it's closest to, and then all you do is you look over each cluster and add up the sum of the distances to the center within each cluster. So you're trying to minimize this quantity. So does this optimization problem make sense? It's a classic problem in approximation algorithms.
Quick question.
Yeah.
So it seems to be the same as K-means. Or what is the difference? Oh, that's the difference.
That's the difference.
Okay.
So for example, K-means is another popular one, which you'd be trying to minimize the sum of squared distances. Another way of saying that is when you do it in things like the Euclidean plane or in higher dimensions, then once you've chosen what your clustering is, the center you would choose would just be the average of the points in the cluster, and you'd be trying to minimize the essentially the sum of variances for each of the clusters. But K-means is a bit different because it's sum of squares. There are lots of other variants you can do, like there's also min-sum clustering is another popular one. There's an endless variety of different objective functions you can define. I still think this is at least one of the most natural ones. But the issue is this problem is hard. Not just NP hard to compute exactly, but it's even hard to approximate within a constant factor. So what's known about the K-median problem? So there's a result of Guha and Color improving on earlier work that shows that it's NP hard to approximate, to not even just get the exactly right answer for K-median, but to approximate the optimum value within this constant factor, 1 plus 1 over e. So there's some universal constant at which you can never hope to get an approximation algorithm better than that constant. And on the algorithmic side, so the best known results actually are fairly recent. Lee and Svensson, who gave a 1 plus square root of 3 approximation algorithm. So of course there's a gap between these two. So a natural question in theory is to try and close this gap, to figure out what the right constant is for the best that you can approximate K-median in general. But there's a path around this sort of hardness. So this is what I mean by when I say hardness is sort of an obstacle that we have to look out for. Because as important as K-median is, and as widely as it's solved in practice, the issue is that in practice, a lot of times you wouldn't even be happy with an approximation algorithm with this type of factor. So what can you do to try and get better approximation algorithms? You can try and understand what about the instance makes it easier. So there was this really influential paper of Balkan which gave a path around the hardness. By doing similar things, by looking at where the problem comes from, to try and devise an understanding of what makes it easier. So the notion which they introduced was something called approximation stability. It turns out to be enough to actually get a p-task for this problem. So let me tell you about what approximation stability is. So the sort of, the basic idea at a high level for approximation stability is that, you shouldn't forget that the optimization problem you've defined, the way you've chosen your metric space, it's an invented problem because it's crafted so that optimizing it should recover some clustering that's close to some ground truth solution. So what if you make the assumption that any near optimal solution should be close to the ground truth? That's, after all, what you're hoping for is that the optimization problem itself should be a good proxy for recovering some ground truth clustering, at least approximately. So approximation stability is about making that more precise. So the first thing that we need is we need a definition of what constitutes when pairs of clusterings are close. So it'll be the natural way that you think about it is just if you're given two different clusterings, you want to try and map which cluster is which, find a matching between their two clusters, which agrees in a large fraction of points. So the way to do this precisely is we'll say that the distance between clusterings S1, S2 up to Sk, and S1 prime, S2 prime up to Sk prime is given by let's say the entire universe of points is n, just for keeping the normalization. Well, what we're going to do is we're going to look at the best matching. So here, pi. Matches, which pairs of clusters should agree. And so we look at the best case matching between the clusters in S and the clusters in S prime. And what we do is for each pair that are supposed to be Si matched to S prime, S of pi I prime, what we do is we look at how many things are in Si but not in S prime. And we add up the sizes and we normalize by how many total points there are in the universe. So this quantity is something between 0 and 1 that measures, how well we can actually couple these two sets of points, what fraction of the points they agree on. So now with this in mind, the sort of key definition which they introduce is this notion of approximation stability, which I alluded to earlier. So we'll say that it's a property of an instance of the problem. We'll say that an instance of k-medium, although this definition could apply equally well to other optimization problems. Yeah?
So to compute the distance between the centers, you use the distance vector.
Yes. Well, but I haven't, so this distance has nothing to do, this is a distance measure between clusterings. So it has nothing to do with the metric space we defined so far.
So is every one of the S1, S2, up to Sk, are those all clusterings, or are those centers of clusters?
Those are clusters. So this would be a partition of the set of S points. This would be a partition of S as well. So what we're doing is we're measuring how close two different partitions are.
And then how
Then how can you compute this I minus this pi I?
These are sets, right? So all I'm doing is I'm taking the elements in one set that are in SI and are not in the set that it's matched to, and I'm measuring the size of those two. But good question. Yep.
Is this symmetric?
So this, I guess, the way they defined it was this way, but maybe a more elegant way to define it is this way, where I would take the symmetric difference between them, and then I should really normalize by 2n here. All of the things won't really change. If you prefer to do it this way, where it's explicitly, symmetric, then this is fine too. But what I mean here is you take all of the elements that are in one but not the other. So that's the symmetric difference. Are there any other questions? Yeah.
In this algorithm, is k known? Like, is the k fixed or is k also?
The k is part of the input. The k is part of the input. I'll get into that later because the definition I'm going to define, there have been further relaxations of what this definition is, which have to do with thinking of k as being unknown. But I'll get into that a little bit later. Yep.
Going back to the number cells, is there anything better for the hardest swimming unique games conjecture?
Nope. This is the best that I know of. Any other questions? That's an interesting question, but there's some problems for which unique games isn't the natural fit. And I'm not sure this should be one where we should get better hardness results based on UGC, but that's a side issue. So now remember, what we need is this definition of approximation stability. So we're going to say that an instance of the problem is 1 plus alpha epsilon approximation stable. If every solution within a 1 plus alpha factor of the optimal value has distance at most epsilon to the optimal clustering. So the idea is that the way we've defined this optimization problem, there's a lot of art at how exactly you would choose the metric space in a lot of applications, right? Think about, for example, when your objects are proteins, how complicated that function should be about, how the actual structure influences the function of the protein. But what we're hoping at the end of the day is that we've defined a metric space which certainly has the property that exactly optimizing it should recover some ground truth clustering. But that's sort of the end of the line there, is that these problems really are hard to approximate. So what if we make a stronger assumption that even nearly optimal solutions should be close to the ground truth? So this is just an assumption about how faithful our representation of the problem is to the actual problem that it's supposed to represent, which is getting something close to true ground truth clustering. So what this says, think of alpha as being a very small parameter greater than 0, is that every solution, which is within a 1 plus alpha factor of opt, and this could be something like 1.01, 1 plus alpha. So it could be much smaller than the currently known hardness approximation results for it. But what we're assuming is that every solution that's close enough in terms of objective value should also be close in terms of its distance as a cluster. It should produce almost the same clustering, with the exception that you need to change maybe an epsilon fraction of the points in terms of which one is mapped to which thing. So this is sort of the key definition. Does this make sense? All right. So, what are the main results that they prove? So they prove a few things. Let me tell you about maybe the easiest one to sort of sketch the intuition for. Well, let's suppose the optimal clustering is S1 to Sk, and these problems become easier thinking about what the distance is between clusterings if you assume that there aren't really small clusters, because then it gets a little bit trickier to define what this distance is and measure it. But an assumption that makes things a little bit easier, although it's not really necessary, is assuming that each cluster has size at least c times epsilon over alpha times n. So it makes up some reasonable fraction. You could think of epsilon as alpha as being actually subconstants themselves. But one of the main results here if the instance of the problem is 1 plus alpha epsilon approximation stable, there is an efficient algorithm, so polynomial time, to find another clustering that is epsilon close to the optimal clustering, S1 to Sk. So that's the main result, is that some notion of the stability of the instance you care about can actually circumvent the hardness of approximation results that you would otherwise be worried about. So let me tell you a little bit about the intuition for this, but this is just meant as a sketch. Yep?
Wait, sorry, we don't have a guarantee about the closeness to the optimum value, right? Just to the...
Exactly.
cluster.
Yes, exactly. So this is just a guarantee about the closeness between the two clusterings in terms of their distance. Are there any other questions about what this means? Yep?
How is the running time clearly has to depend on alpha, right? Is it like a bad dependence or?
It's actually a very good dependence on alpha. I mean, there are other types of guarantees where instead of assuming that each cluster is reasonably large, you make no assumption on the clustering. But then what ends up happening is that your approximation factor is not epsilon close, but it's something like c over alpha times epsilon close. So you end up paying for it here. There are also variants of this that work for k-means and for min-sum clustering. And there are actually even other works on understanding things like Lloyd's algorithm for k-means and proving guarantees like this. So I can tell you a bit more about that at the end, but let me at least sketch the intuition for this. So the key starting point is, how should you exploit approximation stability? So the idea is that under approximation stability, typical points behave well in that their distance to their closest center under the optimal clustering is actually a constant factor smaller than their distance to the second closest center. So it's not as if they could be moved to a different cluster without drastically changing their contribution to the value of the optimization problem. That's the idea. Now, you can't prove that about all points under approximation stability, but you can prove that about most points. So the idea is that under approximation stability, all but an O of epsilon fraction of points satisfy W2 of x minus W of x, I'll define these in a second, is at least alpha W average over epsilon. Now let me define what these things mean. So W of x is the distance to closest center in optimal cluster. So if you take the optimal clustering, whatever centers they produce, C1 to CK, then you look at for a point x what its distance is to the closest center. That's the function W of x. W2 of x is the distance to a second closest center, again in the optimal cluster. So you should think about it as if x was forced to not go to his optimal center, the optimal clustering, then how much would he contribute to the optimization problem? And finally, W average is just equal to 1 over n times the sum over x of W of x. It's just the average distance to your closest center. So the important point is that what makes approximation stability nice is that a typical point, as in all but an epsilon fraction of the points, satisfy the condition that their distance to their second closest center is considerably further than their distance to their closest center. That's the key point. And what I'm going to do is I'm going to give this guy a name. I'm going to call this D critical. That's a bit different than their definition of D critical in the paper, but I think this will be easier to sort of sketch the intuition. So now the idea is we want to exploit this property. Now the way to think about it is that what we're going to do is we're going to call a point. This is the other key definition. We'll call a point good, for lack of a better word, if both W of x is less than, say, D critical over 5, and W2 of x minus W of x is at least D critical. In fact, an even stronger claim is that not only do 1 minus O of epsilon points satisfy this condition, where they have a gap between their second closest and first closest center, in fact, they even satisfy this condition that they have that, and their distance, their true clustering is at most D critical over 5. So this is not a hard sort of claim to prove. And just to complete the notation, we'll call a point bad otherwise. So now actually I can tell you what their main algorithm is. So the basic idea is to construct a graph on the points based on what their pairwise distance is, in such a way that all of the points that are good, now the issue is you don't know which points are good and which points are bad, because these are properties of what their distances are to the optimal cluster centers, and their distances are to their second closest optimal centers. But the key idea is to then define a graph in which all the good points in the same cluster will end up being a clique. And they won't be connected to any of the other good points in another cluster. So let me tell you now how the entire algorithm goes. So we're going to define a graph G, which is on the set of points we're given. So we're given the set S, which are the points in our instance of K median. And what we're going to do is a pair, x, y, where these are just a pair of points from our instance. Form an edge if and only if their distance is at most, let's say, 2/5 of this critical value. So the sort of key points now to sort of finish up are that it follows from sort of a simple application of triangle inequality that all pairs of good points from the same cluster form a clique. That's the first condition. So this is a graph which we're defining just based on the information we have access to. So it's a graph on points, and we're just going to add an edge if their distance is at most some critical value. And now the other key is that there are no edges between good points in different clusters. Yep.
How do we know decrit?
We are given it. Oh. So actually, yeah, so there are ways that you can actually assume that where you can get around assuming you know it, but that's a little bit more of a complicated algorithm. But essentially the idea is, so you have, so if you assume you're given D-critical, which that was a good question, then we define this graph. The idea is, why should these two claims be true? I don't want to spend, a full lecture on this, but just give you an idea of what's going on in these clustering-based approaches. Is, if you have a pair of good points that are in the same cluster, by the definition of what constitutes a good point, their distance from their true center, the one in the optimal solution, is at most D-critical over 5. So simple triangle inequality means that they must be close to each other, close enough that we actually do connect them. And the other side of this is that if you have a pair of points that are both good but are in different clusterings, then you can lower bound the distance between them. Because the distance between them has to be almost the distance between their centers, is the idea. Is that because of this condition on goodness, that his distance to the second closest center must be large, well, it must be at least D-critical, and that other guy is close to his own center, so that actually tells me those 2 points are far, just by applying the triangle inequality. So the sort of remaining catch is that you don't actually know which points are good and bad. So you construct this graph on all of the point sets with the property that all of the good points in the same cluster form a clique, and all of the good points, which are in different clusters, don't connect via an edge. But the important thing is that actually each of these cliques are larger than the total number of bad points, because we assume that each of the sizes is at least something large. So what that tells you then is that you can find whatever are the connected components in some related graph to this, and you can just spit out that cluster. As long as you don't care where the bad points end up going, the fact that you never break up the good points together will allow you to actually output a clustering that's close to the right answer. So this is sort of the main idea of this algorithm, is that, yep?
So you're finding connected components. So what if you have a single bad point that is connected to every clique?
So what you have to do is you actually have to only choose pairs of nodes which have enough common neighbors. So the way to think about it is that pairs that are in the same clique, they for sure have a lower bound on how many common neighbors they have, because each of these clusters is big, and we only subtract off so many bad points that can be completely spurious. And the idea is then that a pair of points which are good but are in different clusters are not actually going to meet that spurious condition, because at most all of the bad points vote the wrong way, and that's still not enough to push it above the threshold. So that's actually that's the sketch of the analysis. The other thing I want to tell you about is that there are a lot of other works along these lines. So are there any questions about the intuition for this clustering result? I'm not expecting you to get all of the details, just the main idea. So one of my other favorite results in this clustering work is some work of Ostrovsky et al., which what they do is they consider instances where the optimal solution on, with k minus 1 centers is actually much larger than the optimal solution on k centers. So what if the instance you're given has the property that there really are k centers, k noticeable components, and they can't be broken up into fewer than that? So what they end up showing sort of informally is that if opt of k minus 1 is at least opt of k over epsilon, so you really can't break up your instance into fewer than k clusters, then what they get is they get a 1 plus square root of epsilon approximation algorithm. So, I'm trying to sort of add these discussion days as a way to sort of give you a flavor of, what else is out there besides some of, the core material. But one of the things I want you guys to think about, and these could be good topics for, the end of the semester or final, project, are there applications in your own research or otherwise that you can think of where, understanding where the instance comes from leads to well-posedness conditions that can give you better algorithms and get you around worst-case hardness results. So I thought I'd at least take a couple minutes if you guys have anything you want to sort of, these are designed to be sort of discussion days. So, any questions about this or, off-the-wall questions about whether you can apply these concepts to other problems, let me know. Yep.
So in the NMF example, you give some evidence that for a typical document database, this separability idea was not so far from the truth,
right,
so as to make the algorithm, your approach relevant. Is there any work on how prevalent this kind of assumption is?
Not in the same vein. So, what I liked about the sort of separability thing is that it's an experiment where you can really say, things are close enough to separable that you're doing as well or better than existing approaches. I think we're going to see different ways to justify some of the theory. That was one sort of type of experiment, but I don't know of anything else that fits into that same type of framework. One of the things that we're going to do a little bit later on when we have, a discussion day a little bit later is, there are popular models like smooth analysis, where you think about, it was designed by Spillman and Tang to understand questions like, when does the simplex method work for LPs? Why does it work so well? We have certainly worst case instances where it's terrible, but for typical instances, it really does seem to work well. So part of the idea there is that, nature really isn't an adversary, that they're not choosing their parameters in some sort of gadget-based construction to mess you up. But as long as there's some randomness in how they're choosing the parameters, even if it's very small compared to the actual magnitude of the entries, then it's enough to push you away from the hard instances. So that'll be sort of a different way to justify it, is to think about nature as not being that contriving, as using that to sort of get you out of worst case hardness. But I don't know of any other, even though there are plenty of examples of conditions which get you out of worst case hardness that are sort of along this vein of being well posed, I don't really know of that many experiments of sort of justifying them in their own right and saying whether or not they happen in the real world. but that's a good question. Was there another question here? Yep.
So I have a question about the experiment for the topic modeling.
Yes.
Right? So the way you stated the experiment that was carried out, you used mallet to topic modeling, and then you generated some synthetic data,
Yep.
and then you showed that NMF performs better than mallet.
Yep.
But could it be possible that mallet just performed bad because it assumes kind of different distribution on the words than like the synthetic distribution that you?
Oh, it actually assumes the same distribution.
It assumes.
Yeah, exactly. It's tuned specifically for LDA models. And actually, the way you set up the hyperparameters, you even cheat even more because you give mallet those parameters, which, those are things typically you have to tune to your collection, but you're even telling it how exactly you generated from an LDA model. So we'll get into that a bit later, that what it's actually doing is it's assuming the same distributional model that you sampled from, but it's using Gibbs sampling to try and fit the parameters. All right, so that's it. So come to me after class if you have further questions about this. But next time we're going to start tensor decompositions. That'll be our next unit.